In this video, I will discuss how to integrate knowledge graphs into the RAG process. The first question we need to consider is why. This is the classic RAG process. Given a question, we retrieve related chunks from the vector database, and then include these chunks in the prompt to call a large language model. To illustrate the necessity of knowledge graphs in this process, let me provide an example. Suppose the user asks, what are the common side effects of cold medications? The user wants to know the side effects of medications used to treat colds. We aim to use the vector database to find relevant information. Imagine the vector database contains a section describing one particular medication, such as cold medicine A. However, this section does not explicitly mention the keyword cold. Without this keyword, the question might fail to match the chunk, as the similarity score would not be high enough. Yet this medication is indeed used to treat colds. Conversely, if we already know that cold medicine is a common treatment for colds, we could use this knowledge to locate the relevant chunks. So, where do these relationships come from? The answer is the knowledge graph. Let's explore how a knowledge graph can solve such problems. First, we define a simple graph. Here, each node represents an entity, and the arrows indicate relationships. For instance, medication 1 and medication 2 can treat colds, and colds themselves have certain symptoms. Now let's consider how this graph can integrate with the RAG process. We revisit the question. One problem we can address is question expansion. For example, when the question mentions common cold medications, we can use the knowledge graph to identify specific medications, such as medication 1 and medication 2. Using this information, we can expand the question to, what are the side effects of common cold medications, such as medication 1 and medication 2? This makes the question more specific. Once the question is expanded, it can proceed through two paths. First, it can query the vector database to retrieve relevant chunks. Second, it can query the knowledge graph to extract a subgraph corresponding to the question. The expanded question now includes key entities such as cold, medication 1, and medication 2. Using these entities, we can locate their corresponding nodes in the graph and extract a subgraph containing these nodes. For example, the relationships for medication 1 and medication 2 indicate their use for colds. These relationships form a subgraph. Next, we combine the subgraph with the retrieved chunks. Since the subgraph is structured data, it cannot be directly merged with the textual data. To address this, we convert the graph into a textual format. The graph consists of multiple triplets, subject, predicate, object, such as colds can be treated with medication 1 and colds can be treated with medication 2. We translate these triplets into text, then merge the textual representation of the graph with the chunks retrieved from the vector database. The combined result continues through the subsequent steps. This approach ensures that the final context includes potential answers. It compensates for cases where the vector database alone might miss critical information. However, this process introduces several challenges. The first challenge is constructing the knowledge graph itself. Creating a graph is often labor-intensive. Traditionally, it was done manually. Nowadays, large language models can assist by constructing graphs from text using prompts. The second challenge is filtering redundant information. Merge results may contain overlap between the vector database and the graph. Post-merge filtering is necessary. The third challenge is extracting subgraphs. For example, the simplest approach is one-hop neighbors, but more comprehensive methods might include two-hop or three-hop neighbors. The more nodes we include, the richer the information, but there is a trade-off in complexity. The fourth challenge is leveraging the subgraph. for further vector database queries. For instance, the subgraph itself can be used to perform additional retrieval, potentially enriching the retrieved information. Finally, integrating structured information into the process remains a challenge. Graphs inherently have structure, unlike the unstructured chunks retrieved from a vector database. Teaching large language models to understand and utilize this structure effectively is difficult. Potential approaches include writing structured prompts, incorporating graph neural network techniques. Despite these challenges, integrating knowledge graphs into RAG can enhance performance by reducing hallucinations and improving context quality. If you're interested in these topics, feel free to leave a comment and let's discuss further.